Okay, please go, sorry.
Okay, hello everyone. It's my great pleasure to introduce the next speaker in this online seminar series, and it'll be Professor Atsuo Kuniba from the University of Tokyo. And as you can see, he will speak on generalized hydrodynamics for randomized box ball system. Thanks, Atsuo.
Thank you for the introduction, and thank you for giving me this opportunity. Can everyone hear my voice and see the screen? Is it working okay?
Yeah.
Yeah, okay, thanks. So let me begin with the question that, are there any 1D deterministic cellular automata with the following features? So the commuting time evolutions, family of conserved quantities, solitons obeying factorized scattering, equation motion given by discrete soliton equations, and Yang-Baxter equation, the beta ansatz. Actually, the answer is no, as a box ball system and its generalization based on quantum groups. And it's provided exact quasi-particle picture to Beta's counting formula for the number of string solutions, and allow interpretation of corner transfer matrices as tau functions, and can identify the beta eigenvalue at Q equals 0 with the Poincare cycle and so on. So the plan of talk is as follows. In the first part of my talk, I will review this basic integrability feature of the BBS. And I think by now this part is quite well known to some community of people. So I'm sorry if you belong to the community. The latter part of my talk, I will discuss about the recent progress on statistical aspect of randomized BBS in out of equilibrium. And more concretely, the limit shape problem of soliton distributions and density plateau emerging from domain war initial conditions. So they can be analyzed by thermodynamic beta ansatz and generalized hydrodynamics. So first, what is n-color box ball system where n is positive integer? So here is an n equals 3 example. So 0 is the empty box, and 1, 2, and 3 are the balls with colors. And the dynamics is as follows in this example. First, you move every ball 3 once, and every ball 2 once, and so on. So what is the rule of the move I? So pick the leftmost ball with color I and move it to the nearest right empty box, and do the same for the other color balls. For example, the first things you have to do is this factor. So you pick up the leftmost 3 and move it to the nearest right empty box here. And so this sits here, and next 3 sits here, and 2, and so on. So if you look at this procedure carefully, it's not difficult to establish that if you have consecutive balls with color satisfying this inequality, then it behaves like solitons like this manner. And the velocity is nothing but amplitude. You can let them collide. So the bigger solitons are faster, as in the real solitons, so they eventually collide, but they nicely come back in the very original amplitude, 3 and 5. This is non-trivial. So the two-body scattering involves an exchange of internal labels or colors, like quarks in hadrons. See, there are solitons, but the internal labels has been changed, like UDS, quarks, and so on. And there's also a phase shift. I mean that if you follow the trajectory of the free asymptotic states, then it gets shifted by the collision. This is very typical things in the integral system. So here is an example of the collision of 3 solitons. I've got the 2 examples here, and I have same list of the solitons in the 2 examples, 3, 2, 1, 3, 1, and 2. But the timing of the collisions are different from this example and this example, but they eventually come up with the same list of the solitons in the asymptotic states. This is again non-trivial. So namely, the Yang-Baxter property is valid. The solitons in the final states are independent of the order of the collisions. So it's a really good reason to believe that this is a really integral system. And there is a decent origin of this integrability, and one can attribute it to the quantum integrability. Yeah, and that's nothing but a solvable lattice model at temperature 0. So what does it mean? So for example, I pick another example of time evolution of the collision of the solitons of amplitude 2 and 1, like this. Now this emerges from the configuration of a 2D lattice model in statistical mechanics like this by forgetting the hidden variables on the horizontal edges. If please remove those messy numbers sitting on the horizontal edges, then you observe this pattern is here, right? But this is a typical situation of the configuration of the two-dimensional vertex models. So the actual thing is, N-color BBS is nothing but a 2D solvable vertex model associated with a quantum group UQSLN plus 1 hat at Q equals 0, where Q plays the role of temperature. Then you can introduce a low transfer matrix in a standard way, but take the Q0 limit. Then there is a very special good gauge that it becomes a deterministic map defined by the unique configuration which survives at Q equals 0. And that gives you the time evolution of the box-ball system. And it actually forms the commuting family, T1, T2, and T infinity. So here you see that you may have, so that it's strange why we have 2 digits here. That corresponds to T2 in the time evolution. You can have any sequence of the numbers that gives you TL for general L. And they are all commuting and non-trivial. So the proper formulation uses Kashiwara's crystal-based theory. That's a theory of the quantum group at Q equals 0. So I said that I set up the solvable lattice model and take Q0 limit afterwards. But you can reverse the order. You can start from the theory of the quantum group at Q equals 0 and start everything, construct everything out of crystal-based theory. I'm not going into such aspects in detail in this talk, but let me just give you some outcomes of such insight. So there are now integral cellular automata with quantum group symmetry. Here is an example associated with an orthogonal group, SO10 hat automaton. So this is an example of the collision of 2 solitons. So here you see that not only balls, but there are letters with bars. So I should probably call them as particles and antiparticles. And they go pair creation and annihilations. Here you see that the amplitude has 5 and 3, and that's also the here. But if you see closely, 2 and 2 bar pair is changed into 3 and 3 bar pair here, non-trivial. And N-color BBS is nothing but the A-type case of this general formulation. And it can also be identified with this orthogonal type without antiparticles. So somehow this class of the generalized BBS is kind of more general and also natural object. And the solitons and scattering, in such a generalized model can most naturally be described in the quantum group framework. That has been all done so far. Anyway, this is a kind of short summary of the content so far. So we have BBS, which is a cellular automaton. And it is coming from the quantum integral system, which is a solvable vertex model by taking a Q equals 0 limit. But also there's another integrability aspect coming from the classical integral system, which I don't get into detail in this talk. But basically you have the soliton equations and take the procedure so-called ultra discretization. And the same things meet here. I mean, the 2 limits have the common limit here. So this is a kind of very good, decent object, as you may guess. And moreover, there is the most powerful approach in the initial value problem here. That's the inverse scattering method. And powerful approach to diagonalize the system, which is known as Beta ansatz. And the Russian group has clarified these as the quantum counterparts or the classical counterparts each other. But then one may ask, then is there any good structure inherited from this Beta structure also in this setting? And the answer is also yes. What is Kgl Bijection? That it asserts the formal completeness of the hypothetical string solutions to the Beta equation at combinatorial level. And its remarkable connection to BBS was discovered after 18 years from the original introduction in 2002. So because this part plays a rather important role in my talk, in the rest of my talk, let me get into somewhat in detail of this aspect. So now you must expect that this is, we are going to the Beta00 stuff. And I picked the oldest example of the Beta00 system, which is a spin 1/2 periodic Heisenberg chain. This is a Hamiltonian. And this is Beta equations for the 6-side chains with 3 down spin sector. So there are 3 unknowns, U1, U2, and U3, and they are solution to this coupled algebra equation, which is the Beta equation. So what is a Kgl bijection? It's a combinatorial analog of the 2 objects. You have the solutions U1 and U2 and U3. Every time you get the solution, there is a recipe to construct eigenvector of the Hamiltonian called beta states. Now the Kgl bijection do this at the level of the combinatorics. How does it go? So here is a solution to the beta equation. There are 5 solutions, and these are complex U-plane where the black dots denote U1, U2, and U3. But actually the U-plane is rotated 90 degrees, so the horizontal axis is the imaginary axis. So you observe certain patterns. So the solution comes with certain strings, so-called strings, which is approximately 2i equidistant distribution of the dots, symmetric with respect to the vertical axis. So there are 2 strings here and 1 string here, like this. So let's visualize it in combinatorially as follows. So here are 2 strings and 1 string, and here as well. But here are 3 strings, length 3 strings, and there is only 1 of them. There are 3 1 strings. Do you know? You understand? And if you have such freedom, then these 3 must be distinguished by these numbers assigned to each row or strings. So that's a kind of simplest example, the Licht configuration. Now, the other side of the bijection, beta states. So it's like this. Because this is a Heisenberg chain, you have the superposition of up and down states, and the length is 6. But because this is in a combinatorial setting, there is no superposition, just monomial, like this. So spin up, down, and align. So this is the simplest example, the Kgl bijection of the 2 combinatorial objects. One is a combinatorial analog of the beta roots. One is a combinatorial analog of the beta vector. Let's formalize this setting into the SLN situation, SLN+1 situation. It's a bijection between highest states and Licht configurations. Here is n equals 3 example. So this is an analog of beta vectors, and this is a beta roots. So in higher rank systems, you have got the color of the beta roots. So there are 3, actually in general, it's nth of Young diagram here. And to distinguish the position of the strings of the equal length, you have to assign certain non-negative integers to each row. So this can be regarded as a box-ball system states, and which accommodate solitons. On the other hand, this levels the correction of strings, and physically the strings correspond to the bound state of magnons. So of course, because this is a mathematical one-to-one correspondence, there is some messy mathematical characterization of both combinatorial objects. I'm not going to describe the details, so you can just you don't have to be bothered about the highest condition on this set. So basically, this you can regard as a box-ball system states with n color. But the Licht configuration plays an important role. So let me explain a bit more detail. So it consists of the 2 data. So red one and blue one. So red one is the nth of Young diagram. This is a list of the length of the strings in the beta equations, beta. And rigging is a number attached to each row of them. And totality of this data is called Licht configuration, but they must obey certain selection rule. And let me introduce this rule. So it's getting into some technical mess, but well, you don't have to be bothered. But anyway, this number is, and this formula will be slightly used later. So I picked up the eighth component of this Licht configuration, like this, and called the number of the lengths I rows as MAI, like this. And there is a rigging attached to this cliff or block of the component, and that obeys this rule. But this rule is very simple. So it's the good thing about this object is there is a very simple formula to count them. So number of rigging choice of the fixed configuration is given by this formula. This is elementary combinatorics like this. But the point is how this upper bound is given, and that's specified like this. So you have the length of the chain times some combination of this data M, and here C is the character matrix. And this is in Beta terminology called hole or vacancy of holes. And this is actually a list of the strings. So the M refers to the strings and H refers to the holes or vacancy. That's kind of standard in Beta notes. But anyway, so this is, although this looks a bit horrible, but it's really decent generalization of Beta's formula for the number of solutions in his very original paper. Here is Beta's paper on page 224. You see that he is trying to count the number of string solutions. And he ends up with the product of binomials of this structure, where this extra kind of addition factor is system size minus twice minimum P and N something. That's exactly this formula for SL2, where character matrix reduced to 2. So this is really kind of good object in combinatorics. Now, so far I haven't explained how the bijection goes, and there is some mathematical or Kgl algorithm. So let me also introduce this algorithm just briefly. I just convey the flavor. So we should get the path or kind of sequence of 0, 1, 1, 2, and 3, and so on from this data out of liquid configuration. Now the algorithm tells you that there are boxes that should be removed. So I marked it by blue. So in this case, I should remove 2 boxes here. And the algorithm is designed so that the result of the removal is again liquid configuration. I mean, satisfy the selection condition. So you can repeat this removal procedure until you end up with trivial liquid configuration. Every time you remove, you record the number of boxes that you have removed minus 1. So removed 2 boxes minus 1 is 2. Removed 3 boxes minus 1 is so 1, 2, and so on. Then reading these red letters backwards, you get the image. So this is recursive and very messy combinatorial procedure, and it's very easy to make mistake. But it's perfectly mathematically well-defined algorithm. So you can program it on computer, and the computer gives the image almost instantly, even for the path of length, say 100. So now I have explained the Kgl bijection. So there is a bijection between paths like this and liquid configuration. That's an nth-Young diagram with associated with leaking. Now here is example of the time evolution of the big box ball system. But basic questions, how does it look like in terms of liquid configuration? Because it's bijection, I can translate the dynamics into the dynamics of the liquid configuration. Here is the result, which is marvelously simple. In what sense? Configuration, namely this Young dynamics remain unchanged. So they are the concept quantity or action variable. On the other hand, this rigging, look at this T dependence, flows linearly. So they place a lot of angle variable. And the Kgl bijection achieves the linearization of the dynamics. In short, liquid configuration is nothing but the action angle variable box ball system. This fact has been noticed in 2002. So in particular, the first Young diagram here has a very simple meaning that it's a list of the amplitude of solitons. Here you see that amplitude is 4, 3, and 2. And Young diagram is 4, 3, and 2. So in this sense, configuration, namely the nth-probe Young diagram, can be regarded as a generalization of the concept amplitude, which I called soliton content. I would like to remove this. But can you see? So this configuration part, nth-probe Young diagram, will be called the soliton content. Now, to motivate the latter part of my talk, namely the randomized situation, let me give you a quiz. What are the soliton contents, or at least their amplitude? starting from these two initial conditions. This is one color BBS, and this is two color BBS. Can you guess? So you see that soliton's amplitude 2, 4, 3, 3. But that's not so really. So if you make time evolution many times, then it turns out the correct list of the amplitude 5, 3, 2, 1, like this. Even if you don't apply this time evolution, Kgl Bijection tells you the answer immediately. But anyway, so this is the correct answer, and which might be non-trivial, just given the initial condition. And similarly for the color two cases, like this. So that motivates a randomized situation, which I now move on. So randomized box-ball system. So recall that we have PBS states like this, and we can apply Kgl bijection to get the soliton content, conserved Young diagrams. And now I randomize these BBS states by introducing the identical and independent measure on each site, like this. So these local states takes, because this is n color BBS, empty box or balls of n kinds of balls. And I assign the probability for each occurring of these situations like this. So PI is control of this IID measure. So this IID measure is n parameter IID measure. Now it induces a non-trivial measure on the set of soliton contents and Young diagrams via this Kgl bijection. So at this level, this is just IID, very simple. But more intrinsic data we know is the conserved Young diagrams. And so the basic question is how this natural simple IID measure is induced up to this measure in the soliton content. And combined with the L infinite limit, then it leads to the so-called limit shape problem. So determine the scaling form of the most probable soliton content when the system size goes to infinity. That's first basic setting of the first main program, right? Now, this can be done by Tba, minimizing the free energy F associated with this probability distribution. So as I said, given the configurations, number of the linked configuration possessing the same configuration can be given by the generalized Beta00 formula like this. Probably you remember this formula. And this factor takes into the account that each site has this IID measure. So this is a fugacity factor essentially. So these temperatures are related to this IID parameter in this manner. So this is a special case of a GGE, generalized Gibbs ensemble with n temperatures. And ZL is the normalization constant, partition functions. So now using this formalism, we can define the free energy. And minimization of the free energy gives the answer to this problem. So let me give you some basic steps and final result. So I introduce a scaled string and whole densities, rho I and sigma I by this formula. Remember that this is number of the color A length I strings in the linked configuration. And I scale it like this, where L is the system size. So this is a string density of color A and length I. Similarly, this is a whole, and the corresponding notation is sigma. And these are related by this formula, which is the scaling form of the previous ones, like this. And from here, technically, I assume this condition for this IID parameters. And now the task is rather kind of standard. So the problem is minimize this, maximize this property under the constraint that like this, applying the Stirling formula and so on. So that leads to the so-called Tba equation of this form. This is a generalized temperature. And curiously, it is expressed only by using this combination ratio of the string and whole densities. This fact is rather well known for the Tba kind of things. So I would call it as a y function, but anyway, so with a boundary condition, which takes into account this behavior like this. So the first task to find the most probable Young diagram is to solve this. And the answer is given by this. Sorry, this is just another form of this Tba equation. So you can take the exponential form of this one, and that's reduced to this so-called constant Y system. Full Y system contains a spectral parameter as well, but in this setting, we don't have spectral parameter, and so this is just algebraic equation, which looks pretty neat, isn't it? Now the solution is given by this formula. So maybe you may feel that this is somewhat some version of a discrete soliton equations, and this is a solution in terms of tau functions. It's really so. So it's like the Qi is a sure function associated with A times I rectangular Young diagram with fugacity parameters in it. Sorry, IID parameters in it. And so this is the usual formula of the kind of wave variable in terms of tau functions. So you may regard like that if you wish. Anyway, this is a closed formula for the solution of the minimality condition of the free energy. But in a problem of the limit shape problem, we have to also determine this hole and strings individually, not only by the ratio. And that must also be done, and that actually can be done. And here is the answer. So the result, the limit shape of the soliton content is given by this formula. So here is again the eighth component from the liquid configuration or configuration. And I remind you that MAI denotes this number of the length I rows here. And in order to determine the limit shape of this Young diagrams, we have to determine the limit shape or scaling form of this length of this red strip. And that strip is this quantity, length of the ice column of mu A. And I take the scaling limit by dividing by the system size and take the limit. And the result is given by, again, expressed by the sure function or tau function, if you wish. That's the result. Another result is scaling behavior of the width of this Young diagram. And that's given by this formula. So it's a logarithmic scaling. So this formula is neat, but contains a sure function with entries pk, where pk is this data. So IID data. See? But if you specialize this pk parameter in this manner, that corresponds to the principal specialization of the sure functions. And these formula becomes quite neat, and further concrete formula can be possible like this. The string density, hole density, and scaled column length, and like this. So these are all theoretical calculations or predictions. And you must check it against the simulation by generating this IID BBS states. And let me show you one such check. So here I generated the ensemble of the two-color BBS states with 1,000 sites with distribution, IID parameters like this. I suppose the summation of these three is 1. Yeah. And vertically scaled by the system size. So here, blue plot is a result of the simulation. I randomly certainly generated IID states and took the image of the Kgl Bijection and plotted the resulting Young diagrams scaled by L inverse factors. That's a blue dot. And the orange plot is a theoretical prediction by Tba, like this, the first Young diagram, the second Young diagram. So the agreement is more or less good. So that's kind of basic kind of example of the limit shape problem. I suppose I'm going pretty fast, so I think I finished in 10 minutes or so. Anyway, so let me come to the final topic. So the generalized hydrodynamics. And from here, I restrict myself to the one color BBS only. So let me remind you the basic equation in Tba analysis. So there is this equation, but because I restricted myself to the one color case, this upper index becomes void. So you can just remove this upper index, and this factor is just removed by 2. And that's this formula, and that's a kind of Beta equation in terms of the Hall and string densities. And now basic addition by the GHD is a speed equation. So VI, by VI, I denote the effective speed of the soliton with amplitude I. So the bare velocity is I, as I showed in the very beginning of my talk. So the amplitude equals to the velocity. So if there is no interaction between solitons, VI is I. But there is also interaction effect. And that is expressed by this factor, where this blue factor 2 minimum ij is a phase shift of the solitons of amplitude I and j. And this factor represents how often the soliton of amplitude I encounters the opponent of the collision with amplitude j, using the density of this j soliton and their velocity, because this frequency depends on the relative velocity of the two solitons. So this is a closed system of the equations for the effective velocity Vi given these densities, which was determined by this limit shape program like this. So I input such results in the so-called limit shape program and try to find the solution to effective solution speed. And then this is the result. Actually, by now, this kind of result has been much more generalized, but this is a kind of simplest example. Right. So somehow, due to the interaction, so the effective speed has get modification from I. So I think if Q equals 0, then this reduced, Vi reduced to I. But so the finite Q effect enters like this. Now, let me introduce the one of the central idea in the GHD, the generalized hydrodynamics. So I mentioned the Tba Y function, which was the ratio of the string and Hall densities. And it satisfies the separated equation. So there is a basic hydrodynamic equations in the standard textbook sense. But once you apply this to the integral system with Beta00 structure, then you observe that the equations are split if you switch onto the Y variables. That's the key idea in the GHD, like this. But this Vi, it must be chosen like this. And this, so as I said, this Tba Y function plays a role of normal mode in the Euler scale hydrodynamics on the integral fluid. So I'm not going to explain the kind of basic setup or general or detail, but kind of this is a general philosophy or a kind of key observation in the development of a GHD, I think, in my personal point of view. Anyway, so we apply this idea to the Riemann problem of the BBS soliton gas. More concretely, describe the profile of the fluid, BBS soliton gas, starting from the homogeneous initial state, except a single discontinuity at some point. So until this point, we were only discussing the BBS in the homogeneous system, just empty background and homogeneous. And well, solitons move to the right and so on, but there's no kind of inhomogeneity, artificial inhomogeneity. But now I introduce this Riemann problem setting. More concretely, we consider the container, infinite container of the BBS soliton gas with one wall here. So here is an empty or vacuum. And here is, this side is full of solitons, BBS solitons. And it is controlled by the density of the ball, P. So there are many lists of the amplitude solitons, but in total, the density of a ball is P. So P is the only parameter of this experiment. And at time t equals 0, I remove this wall. And then the soliton gas expands. And what happens, can you guess? Well, the answer is written on the top, on the first line of the page. But what we observe is like this. R is a space coordinate. Why it happens, well, let me explain. But anyway, so first I must say that this plateaus broaden linearly in time. That's natural because solitons are just moving, proceed to the right, depending on the effective velocity and so on. So that the gas expands. And that means that plateaus broaden linearly in time. So this linearity is a kind of manifestation of the ballistic propagation. But anyway, linearly in time. So it's interesting to observe the universal curve with respect to this variable, which I call Rate variable, zeta. Then this curve collapses onto the single curve, independent, like this. I will show you the data later. And the basic problem is to determine the kind of profile of this universal curve, namely the hk and zeta k. So zeta k is the position of the plateau, h, and hk is the height of the case plateau, where k is the level of the plateau counted from the left. Now, before giving the answer or the result from GHD, let me explain further why this is happening. I think you can guess. So actually, to each plateau, there is associated a particular list of the amplitude of the contributing solitons. For example, let's look at this place position. So after removal of the walls, soliton starts to go to the right at their own velocities, possibly with interactions, but shorter solitons or smaller solitons are slower. So for example, solitons with amplitude 1 and 2 cannot still reach at this region, this region. And if you look at more and more right, then the soliton must be larger and larger. They must have faster and faster, right? So there are particular subset of the list of the solitons which contribute to each plateaus. Once you know such kind of list of the solitons, then you can apply the GHD. So GHD, as I said, so once you move on to the Y variable, then it tells you that how you can make the proper conjunction of the two homogeneous system in order not to breaking this equation formally. Well, any of this is difficult, but then let me just give you the result like this. So this is a result where Q is related to this density parameter like this. And this notation Q is consistent with this Q, this Q. Yeah, and let me show you the check. So this is example simulation using based on 50,000 samples. And orange plot is the result of the simulation, and dotted lines are theoretical prediction, namely this formula. And they show very good agreement. But if you look at this figure more closely, then you see that the plateau H is not sharp, strictly sharp, rigid, not right angle, but exhibits certain slight broad. I said that ballistic propagation, which is just linear in time, but this broadening is due to the diffusive correction to the ballistic picture, and which may be viewed as a finite effect. And actually, there is GHD also makes it possible to predict this broadening properly or quantitatively. So this is the final topic. So this is a zoom onto the plateau edge, a step around for some particular plateau edge. And so if you magnify the horizontal axis, then we certainly observe that a broadening of the plateau edge like this. This is time scale. And on general grounds, we expect that this broadening is diffusive effect. Namely, this broadening is proportional to the inverse of the square root of t, where this proportionality constant is very important diffusion constant. And in terms of this diffusion constant, the formula should be given in the vicinity of this plateau H like this. For the amplitude of J solitons, density around the case plateau, the meaning of K, around the H, I missed the T here. Yeah, like this. Under the time evolution TL, I haven't explained the TL properly, sorry. But anyway, there are commuting time evolution that I mentioned before. See, so there are index labeling like plateaus and time evolutions and broadening formula, which should be valid in the vicinity of this plateau H. this is complementary error function. So this is kind of minus tangent hyperbolic. So differentiate on this is Gaussian, so that's a diffusive, like this. So this kind of formula should fit this formula if we switch on to the proper scaling variables. And the most important most important things about this fitting is to find the correct formula, this diffusion constant. And this is can be also obtained exactly by GHD like this. So if I substitute this into this and plot this again with respect to this scaling variable, then that should, everything must collapse onto a single curve, right? And here is the result. So this, if you, maybe I should magnify. So this zigzag curve is simulations, and red curve is GHD theoretical prediction. So the agreement is rather good. So this is almost end of my talk. So let me summarize. So BBS is a Yang-Baxter integrable cellular automaton with explicit action angle variables originating in beta strings. Limit shape of soliton content in randomized BBS is determined by Tba. Density plateau emerging from domain wall initial condition is analytically described by GHD. Those are the main results. And here are some kind of capricious pickup of the reference, I'm sorry, but now we are, actually I should say that the latter part of my talk is based on these collaborations. And the latest one is the higher rank version of this GHD analysis, which is almost done. And I expect that we upload a new preprint pretty soon on the archive about so-called complete BBS. You will see. Anyway, this is the end. Thank you for your attention.
Okay, thanks very much. Atsuo, a very interesting talk. We have time for questions.
May I? This is Nalini. May I just ask a very quick question? I am wondering about the fact that there are ultra-discrete systems in one dimension lower than the soliton ones, which are often called ultra-discrete discrete Panové equations. And I was intrigued by what you said about the relationship to the beta ansatz and so on. I just wondered where that one dimension lower system fits in this picture. So on the right-hand side of the slide you're showing right now. Yes, that's my question.
You mean this part?
Yes.
One-dimensional lower system?
Yes.
Well, not very sure, but well, so you see that there are two-dimensional solvable vertex models, yes, like this, but yes, if you take the so-called Hamiltonian version of this system, that becomes one-dimensional quantum system. That's already yes, one-dimensional reduction. But maybe you are saying further reduction. So that's zero-dimensional, one-side problem. So I'm not sure, but maybe you can set up some very interesting zero-dimensional one-side problem. And that's maybe Mari has, the system Mari has golden model.
I'm not sure that they'll be zero-dimensional because I'm thinking of the discrete Panové equations, the cellular automaton version of the Panové equations. So there's still one dimension in time. But it's very intriguing for me to see whether there's a physical interpretation in this context. Thank you for a very interesting talk.
Yeah, maybe I should add one more thing. So this is most classical description with two-dimensional lattice. And so maybe you can regard this vertical axis as a time axis. So then you have a bunch of dependent variable depending on site index, and they grow with time. Yeah, and but probably if you want further reduction, you just consider single site problems, that sort of things. So, but anyway, yeah. From 2D to, if you go from 2D to 1D, then the things get kind of quantum. Yeah.
I see.
Yeah.
Thank you.
Yeah, thanks.
I'm sorry that I have to leave a bit early because I have a class to give directly after this.
No problem. Yeah, good to see you again.
Yes.
Any other questions?
What is the interpretation of that randomized system in terms of these, cellular automatons and betas and Kgl and so on.
Okay, so yeah, I haven't invented a kind of microscopic reasoning model which leads to this randomization. But what I did is just introduce a measure on the state of the space of the BBS. And this measure is pretty simple. So at every site, I put the ball with probability 0.3 and empty 0.7 and so on, independently to each site. So somehow it's a randomized ensemble of the BBS states. And then what I was telling that in such situations, randomization of the states means the randomization of the action angle variables. And that includes a kind of probability measure on the Young diagrams. And you know, the Young limit shape problem of Young diagrams is kind of famous and well studied in many respects. But this is a kind of new kind of such example which hasn't been studied. And there is a good physical meaning that it's a list of the amplitude of BBS solitons. So if you randomize site by site, like probability 0.3 for the balls and 0.7 for the empty sites, then you would like to know that what sort of probability measure is induced for the list of the amplitude of solitons. And what I did is kind of determine the limit shape of this Young diagram. So I haven't invented a microscopic algorithm leading to this randomization, but I just kind of introduced the kind of randomness by hand. And actually, it's possible to introduce more kind of randomness that's called so-called the GGE, Generalized Gibbs ensemble. As I mentioned, this only includes the n kind of temperature because there are only n kind of balls. But actually, the conserved quantity, list of the quantity is much richer because Young diagrams are conserved. So you can attach more general, consider the more general ensembles, GG ensembles with more temperatures and try to repeat, generalize this analysis further. And that can partly be done. And actually, there is some appendix in a paper about that. But yeah, so here I just explained the simplest situation. So did I answer your question? Sorry.
Yeah. Well, hey, I have to consider. Thank you.
Okay, yeah. Maybe we can talk personally after the session.
Yeah.
I might jump in with a question. So you calculated this speed equation for the one color case. What about the more general n color case? Have you?
Yeah, here is the preprint.
Okay.
Yeah, I expected such question. So basically, formula is like this. So it's expressed by the logarithmic derivative of the Q functions, and and in general, so expressed like this. So yeah, general result is there's some logarithmic derivative of the deformed Q character or something like that.
Mm-hmm. Yeah, quite complicated.
Yeah, but kind of interesting. Yeah. So this is the simplest case example.
Yeah. That was my question. Are there any other questions?
May I, Professor Kuniba, how does it look two-color BBS?
Mm-hmm. Two-color BBS.
Yeah, do you have example here? No, you don't have example.
Well, so from here, GHD, I restricted myself to the single color case. And would you like to see some result about the two color cases and the GHD?
Yeah.
Yeah, so that's in the kind of preprint. And well, very preprint. And here is some, well, sorry, there is no plot yet, but there are some, yeah, formulas about the effective velocities, as Mari asked, and also the comparison of the simulation and theoretical prediction with some good agreement. So maybe, sorry, I missed the plot for this case. But in this case, things are much more kind of involved. So solitons has not only the amplitude, but colors. So you have to look at each solitons, which color soliton and which amplitude solitons. And depending on the soliton, you look at the density profiles are different, but they obey certain this DHD prediction. So somehow this is a kind of justification of a GHD approach. Yeah, that's the result so far.
One more question is, can you explain how a Riemann problem is defined for the BBI soliton?
Okay.
The Riemann problem.
So pictorially, it's like this. So we consider the infinite system, and initially we prepare the system with IID distribution on the left side. So the infinite system, and the left of the origin is you prepare it in the IID distribution. Just randomly put the poles with probability 0.3 at the side and 0.7, and so on. Randomize the situation. That's soliton gas here. And the other part is kept empty. That's the initial condition. Very strange domain wall initial condition. And then I remove this word. That means I apply the BBS dynamics starting from this initial condition. And then what happened is the plateaus, density plateau in the density profile. And the problem is to describe is this universal curve, I mean these data HK and zeta k analytically. That's a Riemann problem. And also describe this diffusive broadening quantitatively. Those are the Riemann problem in this setting. And that can be also done for the higher rank case. Yeah.
Okay, thank you.
Yeah, maybe I went too quick, sorry.
No, your timing was very good. We had plenty of questions. Are there any more before we conclude?
Can I ask one question?
Yes.
Please show the page where you introduce the hydrodynamic differential equation for yi.
Yeah.
Yes. So my question is, what is the coordinate of t and x here?
That's a good question.
Is t the same as the time in Boxer system? And what is x?
Sorry, this x was denoted by r in this setting. I'm sorry. This is a space-time coordinate. So originally in the solution of the beta TBA, there is no space-time coordinates, of course. But so now we put in a hydrodynamic situation. Then we expect that everything smoothly depending on x and t. That's a setting of the GHD. Yeah. And you set up the kind of hydrodynamic equation in the textbook sense using this Beta structure. And the point is what sort of variable you should look at. And that's one of the basic key idea in GHD. If you look at y variable defined by this, then the equation splits. But this splitting is kind of formal splitting as in the Beta system. You see the Beta spectrum is just the free particles, but actually those free particle pairs are interconnected by the Beta equations. These things are similar. So this is apparently split with respect to I, amplitude of soliton I, but this VI is kind of couples, and this YI is kind of also couples. Yeah, so this is non-trivial to solve this equation, and I skipped certain procedure, but if you apply it to the ballistic scaling, then X and T is just reduced to a single variable zeta, like this, zeta. And in order to satisfy this equation, nevertheless, for this jump discontinuity, there is some kind of analytic conjunction problem, connection problem between the homogeneous region and another homogeneous region. Some kind of boundary or connection problem. And then you must adjust those GHD parameters properly. And that is enough to determine this shape of the universal curve in that manner. That's a kind of detailed part of the GHD. Yeah.
So do you mean that homogeneous part is the plateau or?
Yes, so this is a homogeneous part, another homogeneous part.
I see. You mean
but we know a priori that these are occupied by solitons with limited list of amplitude. Yes. We input this knowledge into the GHD. So this is the solution when we know that there are all kinds of solitons. See? Solitons with amplitude 1, 2, and 3. But here we have to solve the similar equations, assuming that there are two solitons, 1 and 2 solitons are missing.
I see.
And here only one soliton is missing. So we have a solution with this speed equation, so on here and here independently. These solutions are different, but you must properly make the conjunction of these solutions at here. See? Yes. And these conditions are enough to determine these things. That's the basic strategy of GHD. Yeah. So somehow it tells you how to properly connect the piecewise homogeneous system, and within each piecewise homogeneous system, you have to solve the kind of these equations. Right?
I see. So you did assume such a condition.
Yeah. So well, this is kind of assumed, but yeah.
Yes. Yeah. So maybe in the next page or next to the next page, you show the comparison between how to say the solution and computer simulation.
Yeah.
So you mean that this agreement shows that your assumption was good.
Right. Yeah.
I see. Good. Yeah. I understand.
But it's kind of it's mathematically it's assumption, but we see that this kind of this is an increasing function of I. So the larger solitons remains first in such situation. So it's natural to expect such scenario. So here, because in this region, there is an infinite supply from this container left out of the container. So all solitons are here. But first soliton is too slow to reach this region and so on. Yeah, so this is pretty natural. But actually, if we consider higher rank case, this list was very curious pattern. So that's another interesting aspect of the higher rank models. Yeah.
I see. Thank you.
Yeah, that's partly you have to check numerically. Yeah.
I see.
But once checked numerically, then we can set up analytical answer and can check the agreement.
Thank you.
Okay, then I'd like to thank everyone for their questions and for attending, and thanks to our speaker again. That's all right. Thank you very much.
Thank you. Thank you.
I'm stopping the recording now.
Good. Thanks, George.